Hi, I'm Adi Kanakan, and I'm going to present our paper titled StretchBEV, Stretching Future Instance Prediction, Spatially and Temporally. This is a joint work with Fatma Güney. In this paper, we tackle the problem of future instance segmentation in bird's eye view representation. The problem can be defined as, for a given set of multi-camera images, the task is to predict the future in BEV. This problem has several challenges. One of them is the uncertainty of the future. Since there are multiple possible futures, the models needs to consider all of them. Also, the problem is really high dimensional. Both the output and the input representations are really large because we are predicting into multiple time frames. Another problem is that the problem requires the complete scene understanding. The models needs to understand objects and their relations with each other as well as map elements. As a backbone, we select Leaf Splat Shoot. Leaf Splat Shoot generates current time BEV representation from a multi-camera view. It's a 3D aware network. It simply creates a cost volume by multiplying features and the discrete depth values. As a baseline, we select Fiery. Fiery is a joint perception and prediction method. It's the first work to propose feature and segmentation task in bird's eye view representation. It creates multimodal feature predictions. Fiery has several modules, but we will focus on the distribution generation module here. This module has only one distribution for all time steps. This is problematic because it is limited in terms of generating both diverse predictions as well as accurate results over longer time spans. In this graph, you will see video panoptic quality versus future times to predict. The performance drops across longer time horizons. To tackle this problem, we propose StretchBEV. StretchBEV uses time-dependent distributions, where we sample a different distribution for each time step, as well as we formulate the problem as a state prediction instead of future instance prediction. We separate the dynamics and generations through a state-space model, and we learn the temporal dynamics through residual updates in the latent space. In StretchBEV, we first encode the BEV states created by LSS into a smaller dimension. After that, we create the first intermediate state using a Gaussian distribution. After, we learn a posterior distribution from the future states, as well as a prior distribution from the current state, and we use one of them to predict the future states using a residual update. At the end, all of the intermediate states Y's are decoded back to bird's eye view states using a separate decoder. We also have a model called StretchBEV-P. In StretchBEV-P, we use labels in the posterior distribution as they are used in the Fiery's posteriors. In this slide, we show the qualitative results from nuisance datasets. We compare our method to Fiery, and as you can see, our generations are more accurate compared to Fiery. In this slide, we show the diversity of the examples from Fiery and StretchBEV-P. As you can see, our model can predict different features for a given sample. In this slide, we show the video panoptic quality versus future times to predict. On the left, you will see Fiery. On the right, you will see our model StretchBEV-P. As you can see from the graphs, our model outperforms Fiery for all future time steps to predict. To conclude, our model can generate long-term diverse results using time-dependent distributions. It uses label information for the posterior distribution, which improve the performance. We learn the temporal dynamics through residual updates in the latent space, and it is efficient because we separate the dynamics and generation as we use state-space model. As a future work, we plan to use scheduled sampling to close the gap between posterior and prior distributions, to remove the dependency on the labels in the posterior distribution. And we plan to explore driving strategies using the predicted states in the reinforcement learning. For the animated samples, you can visit our website.